First, I would like to thank the organizers to provide me such a nice opportunity to give this presentation. Actually, I was thinking about a little bit different object with what introduced by Tony and Yuli in this morning, and I'm thinking about real toric objects, especially real moment-angle complex. And last time I talked with Ishida in Osaka City University, and he introduced me some thing about the characterization of smooth moment-angle manifold. So I began to think about this problem, and I got some result. Okay, so to start with, we need to introduce something about what is a moment-angle manifold. Usually it's defined by, actually it's a moment-angle complex, and it's already introduced by a lot of people, and so I will skip the definition of moment-angle complex. And okay, so we pay attention to the situation when it is homeomorphic to a topological manifold. Actually, it can be embedded in some space, but the embedding is not smooth. So I used the expression that it is homeomorphic to some manifold, not just give a chart that to make it into a manifold with some properties. So first, let's look at the topological category, and a sufficient condition is given by Butzberger and Panov, that is when the geometric realization of K is homeomorphic to a sphere, then it is topological manifold. And for the smooth situation, it is a classical result that when K is a dual to a simple convex polytop, then it can be given a smooth structure. And a more recent result by Panov and Justinovsky tells that K can be an underlying complex of a complete simplicial fine. But these two conditions are just sufficient. Sufficient conditions. This characterization in both situations is not complete. And in both situations, for the smooth case, these are all piecewise linear spheres. So, okay, that means after some subdivision, this if K is induced from a complete simplicial fan, after some subdivisions, it will become a standard boundary of convex polytop. But in general, if we don't do the subdivision, this is not the situation. Okay, so let's look at another description of polytopal moment-angle complex, that is when K is induced from a convex polytop. Of course, this is introduced by Bossieux and Mearsman and other experts. So a quick way to see this is that we can embed K, realization of K, in some Euclidean space, and we take the vertex vectors, and then we can do the Gale transform on these vertices. Then we get something like, yes, of course, we get another tuple of vectors, and if we take the real quadrics in this form, then it will become automatically transverse, because case satisfy these properties. And so it is a smooth manifold embedded in the Euclidean space CM. Okay, so now we have two models on this object. One is introduced in this morning, that this is the polyhedral product, and the other is what I have deduced. What we have deduced, it is from some intersection of quadrics, and they can be related. Use a very useful construction that is called the basic construction. It is introduced by Davis and Januszkiewicz from earlier works on reflection group. So their relation can be read in this way. From these quadrics, we can get a map that send each modulus of Zi, the square of the modulus, to Ri, and then we get a linear equation like this, such that each Ri is non-negative. So, and we can see that this pi is invariant under the action of the torus. So let's take example of this. Okay. So when we take K is the 1, 2 with M equals 2, and of course we have the empty set, and the respective real moment angle complex, which is a subspace of the moment angle complex, it can be described by this way. And if we take the quadrics, the real quadrics, we have no further quadrics, so we just have the standard sphere. It's like this. And the basic construction is using the reflection group. First, we have this space in this part. Then we can reflect it across these two these two coordinates to get this space. So in this picture, the three model, I call this three models because they are induced from completely different field. And the third one and the first one was related by the second one. But in this picture, the three models can be put together. And note that the corresponding real construction is perfectly compatible with the complex one. So we can just observe the real one to deduce the information of the complex case. Okay. But that map pi construct in this way, this is not so perfect because it's not piecewise differentiable. That means if we take the inverse map of this map, we need to take the square root, which is not smooth at some point. So this picture shows how points are related. If we use this map, then this line is not so smooth around these 4 points. But we have a more natural map. That is, we can make this line straight and use the radial projections. So this map is piecewise differentiable, and so I first considered this kind of map instead of the original pi. But to get this map in general, we need to do more work. So I read the paper of Bossu and Meersman again, and I found that this they gave a foliation, and we can use this to construct the desired map. Okay, so we have introduced some real quadrics from the Gale transform form of some k, and in general we can get the feature of these quadrics and define them from a general way that it must satisfy two extra conditions. It's called Siegel condition, weak hyperbolicity condition. Notice that these two conditions are all stated in a combinatorial way. And first we can ignore this. And the important thing is that when we get a tuple like this, we can define a foliation given by this action. This is very natural and by exponential functions. So it has very nice properties. And in this foliation, there are two kinds of leaves. One is called Siegel leaf, and the other is called Polytopal leaf. So we distinguish them by whether the origin is in the closure of a leaf. This is introduced by many. The name is actually from the work of Camacho, Kuiper, and Pors. And actually, Polytopal and Siegel, they have done something about these leaves. Okay, I borrowed this example from a previous work. So this map, this foliation, that is the action of T, of R actually. It's quite similar with the one introduced by Yuri in the previous work. But in this situation, everything is in the real space. So the two types of leaves, we can see it in this picture. This is a very nice example. And to get further results, we need some more information about the tuple and the Siegel leaf. We need some characterization. The first one is why the Siegel and hyperbolicity condition. Actually, they are nothing more than the condition that this quadrics defined by these two equations, this one and this one, the intersection is transverse. If we want the intersection is transverse, then this must be admissible. That means it satisfies the previous two conditions. So we can use this to be the definition. That is, it is transverse intersection of real quadrics. So this is very natural. And another one is the characterization of the Siegel leaves. Surprisingly, it coincides with the complement of coordinate subspace arrangement just introduced by Yuri. And so that means if the non-zero entries of Z, we take it as IZ, then if a point is in the Siegel leaf, the orbit of the point is a Siegel leaf, if and only if this IZ, the origin is in the convex hull of the vectors that is in this indexed by those indices from IZ. Okay, but this is not the full story. And okay, I use this notation, an XAP. That is the intersection of this. This is no longer quadrics in general, but when P equals 2, we get the quadric as we have shown at the beginning. And Bossier and Meerman, they proved that this space, that is configuration space, and all Siegel leaves can be completely determined by the smooth manifold and the action T and non-negative real numbers, positive real numbers R. So that means as a fiber bundle, this bundle is trivial, and we can understand this space from this product. And actually, they obtained this by showing that so, okay, this is in the Siegel leaf. So if a point is in the in SA, then we have a unique vector in RD such that it satisfies this equation. So that means from SA to RD, there is a smooth function that corresponds to the solution of this equation. And we can imagine that when we take the sphere, then what is the picture in RD? So the original proof of the original proof of this theorem is by showing that this projection is something like the image of this map. It's something like a polytopal and it's compact. So we can get this one, this characterization theorem. Okay, so that's so I repeat what I want. In the picture I showed where I want to use the radial projection instead of the one we have used in the previous work to get the relation between the three models. So when we change, it turns out that when we change the norm, the secret lies if we change the norm, we can get this relation just like the radial projection, which changing the norm of each point. Okay, even if we change the 2 to general P, we can get a similar result. That is, this SA can be also described by this product. And moreover, there is something interesting that if we denote pi1 to be the projection on XAP, then we have a continuous path, which is parametrized by P. And it is a path in SA, as we have shown in this picture. So if we change the norm, P, this will be more close to the moment angle complex. Okay, this seems the end of the story, that if we take P equals 1, then we get the equivalence of the universal basic construction, that is Davis-Young's cavity construction, and the XA2. That's what we want. But it is natural to think that when P tend to infinity, what will happen? Okay. First, as everyone can guess, we should get the moment angle complex again. And then we take the infinity norm, that is the maximal norm. And when this is done, the first proposition we can prove that indeed this path, which we defined in the previous homeomorphism parametrized by P. The limit point when P tends to infinity must lie in this space. But we cannot eliminate the situation that this is a limit cycle. It's something like this, maybe. But we need to eliminate this situation. So this can be done by add another condition that A is the admissible tuple is centered at the origin. I would like to say something about this condition. Actually, I guess that in general this is still true, but I cannot prove it. When we add this extra condition, we can use scale transform, and we can use a result of Panov and Ustinovsky to deduce that this is indeed the case. That means the Siegel leaf will intersect with the real quadric and the moment angle complex at exactly one point. So we can use similar technique to show that, okay, this is the case. Okay, the result is if we add this extra condition, we can get a similar result that this SA, the complement of some coordinate subspace arrangement, is a product space like that. And in general, even if K is not induced from A, there's a homotopy equivalent between the moment angle complex and SA. This is proved by Bootstrap and Panov. Okay, after that was done, I thought that it was almost finished, but when I think about the rigidity theorem of Bourdieu and Meersman again, I think that we can do something for this theorem, but we have to add restriction that A must be centered at the origin. Actually, this is not such a strong restriction, because we can always find a standard form that is smoothly homomorphic to a general case. In this sense, we can use Ehresmann's lemma to do that. This is not difficult to prove. Okay, we can try to prove the rigidity theorem, which seems quite natural when we consider the corresponding moment angle complexes. This is almost trivial. So if we have a permutation of coordinates from M to M, from M to itself, then we must have a homeomorphism here. And by previous theorems, we have this homeomorphism, and this is the inclusion, and this is diffeomorphism, and this is smooth retraction of Bourdieu and Meersman, and we have a smooth map, which is a homeomorphism, and we can interchange the two objects to get the inverse map, which is also smooth. Actually, if we have this, we don't have this picture, we can also think about this picture. But the difficult point that is how to show that this is a homeomorphism and how to get the inverse map. Okay. So I will go back to the first problem I mentioned at the beginning. Note that if we restrict everything to the real case, this foliation given by this, if we restrict everything to be a real coordinate, we will get everything work in the real case. The rigidity theorem I mentioned just now, in the real case, it's proved by other techniques from Coxity orbifolds by Davis and some other people, and they use the language of orbifolds, and yeah, this is another story, but we can use the same technique to prove in the real case. And what I want to say now is, if we use that projection, we can indeed get some better property like this. So this map is piecewise differentiable, right? Then if we restrict to the real moment angle complex, and we will get a piecewise differentiable map from real moment angle complex to the smooth link like that. So according to a theorem of Whitehead, the smooth structure and the piecewise linear structure are related on if the smoothing is piecewise differentiable. So this will be helpful if we consider the smooth structure and piecewise linear structure. Piecewise linear structure is actually a topological invariant. That is, a topological space can have different piecewise linear structures. And okay, so if we have another piecewise linear structure and we can smooth it, that means we have another smooth structure for the real link like that. And I want to say something about this map. So first we have, if we use this norm, if we use this 2 norm, we will get some picture of the unique solution of this equation. And if we use P norm, we will get the solution of there is a unique solution to satisfy this equation, and we will get a map from the standard sphere to RD, which is the shape of its image should change. And I guess that we will get a polytop and some geometry of the manifold, that is the link, is related to the image of this, something like a polytop, but I cannot imagine what its shape. So, okay, I think I should stop here. Thank you very much for your attention.